So let's go ahead and start questions. I'll go in order, so we'll start with number 11. As a reminder, we're talking implicit differentiation, so the idea is the same. We are still looking at how to derive something. In this case, though, guys, the idea is we're deriving with respect to more than one variable at a time. We have an equation with more than one variable in it, or an equation where it's difficult to isolate the y. Let's look at number 11 first. Here we go. 11. Sine x plus 2 cosine 2y equals 1. All right. First step, I'm going to take the derivative of this function with respect to the variable x. So d dx. So again, this basically takes each one of these and does a derivative property. So we're going to take derivative with respect to x. Wow. Slow down. We're going to take a derivative with respect to x of sine. We're going to take a derivative with respect to 2 cosine of 2y. And we're going to take a derivative with respect to x of 1. Let's do it one piece at a time. A derivative of sine. Cosine. And since it is x, it would just be cosine x. Plus, the 2 is a constant. We're going to move it out. The derivative of cosine of 2y. So focus one piece at a time. Derivative of the cosine. Negative sine. Inside stays the same, but we follow the chain rule. Chain rule says we take the derivative of the inside function. In this case, 2y prime. The derivative of the 2 as a constant can be taken out. The derivative of the y prime. Equals 0. The derivative of 1 is, of course, 0. Now I'm going to simplify what I can. At this point, my goal becomes to get y prime by itself. So start by simplifying. The cosine of x stays cosine x. Okay, so 2 negative 2, so that'd be minus 4 sine of 2y times y prime equals 0. All this stuff is pretty nice so far. Taking the derivative implicitly. Again, it follows the same derivative rules with x, except in this case there's a y involved. So anytime you take the derivative of the y, you will end up with a y prime. The derivative of 2y becomes 2y prime. All right, I want to get y prime by itself. Next step. I can subtract cosine x, that's fine. And I would negative 4 sine 2y times y prime equals negative cosine of x. Divided by the negative 4 sine of 2y. So I end up with y prime equals negative cosine x on top over negative 4 sine of 2y on bottom. The negatives should cancel. Now you might be tempted to rewrite cosine over sine. Don't. Because they have different variables in them, one has an x in them, the other has a y in them, they do not combine in any way. If they were cosine on top with x and sine on bottom with y, you can't combine those. They have to have the same variable to use any of the trig functions. So our goal was, for these ones, define as it refers to it, dy dx, but that just means y prime. This is dy dx. So there is my derivative. And again, the big difference between this and standard functions is A, it's very difficult to get y isolated. I end up having to use an inverse function if I want to do that from trig. But we don't have any rules to find the derivative of an inverse function yet. Do they exist? Yes. And the other big difference is y prime now contains y in it. So to plug it in, I have to plug in both values, x and y, not just the x value. Let's take a look at what my function look like using Desmos. There we go. Original function was sine of x plus 2 cosine 2y equals 1. Oh yeah. Common helix formations. What I love is the fact that they end up having gaps sometimes. This is a rendering thing. So, obviously this breaks all of your standard function rules, like the vertical line test would fail, so that's why we can't use the standard derivative rules. We have to use an implicit differentiation. Make sure, though, the same rules apply. The derivative of sine is still cosine. The derivative of cosine is still sine. It's just whenever there's a y involved, I will inevitably end up with a y prime at some point if I follow my rules correctly. Questions? Number 11. Let's move to number 13. Same process, same concept. Let's take a look. 13. Sine of x is equal to x times 1 plus tangent y. We have sine of x is equal to x times 1 plus tangent y. It's a good indication that you will be forced to use implicit differentiation if you end up with y inside of a larger function. That does not mean it's the only way or even the best way, but it does mean it's an option. As a reminder from last week, implicit differentiation does not replace the other rules. It's an extension of the other rules. It's adding bonuses. You can do more things that we couldn't have done before. Like if we want to do this with our standard rules, you can't. It can't be done unless you can get y by itself. But that is an incredibly difficult task and not one that many of us are probably very comfortable with. Implicit differentiation gets around it. So, first step, take a derivative with respect to x. So take this function, d dx. Now, before I take the derivative on the inside, I could choose to distribute the x to both terms. That's the best I can get here. Wiki asked the question, would it make it simpler? I think so, but that's because I don't want to do the product rule. And this kind of gets around some of the product rule. It really, really, really depends. So do you want to try it? Yeah. Okay. So this would become, I'm going to write it down here, sine of x is equal to, so the x would times 1, so I just get x, plus x times tangent would be x tangent y. So we got rid of one part of the product rule, but we still have a product right there. So we made it a little simpler. We could argue, but I think either one's okay. All right, let's take a derivative. One more time. Take a derivative of each component now. Derivative of sine. Cosine. The derivative of x by itself. Okay, now we have a product. So I'm going to list out my product pieces. I have my left-hand piece, which is x. I need left prime, which would be 1. My right-hand piece, which is tangent y. Thank you, Ricky. And the right-hand prime piece, secant squared y times y prime. Remember, the derivative of tangent is secant squared. Because it's a y, I will inevitably have a y prime. So let's do this. Left d right plus right d left. Left d right plus right tangent y d left 1. All right. I have successfully taken the derivative. Woo-wee! My goal. Y prime needs to be by itself. Suggestions. How am I going to do that? Subtract tangent y. Subtract that piece. And the 1. Okay, good start. Good start. Let's start there. So I'd have cosine of x minus tangent y. The 1 would be absorbed by the tangent. Minus 1 equals x times secant squared y times y prime. Very good start. Divide. X and secant squared y. And then with y prime is equal to, on top, cosine of x minus tangent of y minus 1 all over x secant squared y. And that would be my solution. For dy dx, as we call it, y prime. Let's go back to Desmos. Okay. Our original function was, why did I do that? I thought that was good. Okay. Sine of x is equal to, any guesses? I mean, we've had, from last week, we had weird, like, circular shapes. We had the helixes. Any, no, I have no guess either. So. X, parentheses, 1 plus tangent y. That's both cooler and a lot less cool than I was hoping for. The derivative? So if I want to determine the slope of what's happening right here, which Desmos does not like selecting individual points, I found when they break this rule. So at the point what looks to be at 2, negative 1/2, or pretty close to it. If I want to use that particular point, I'd have to plug both those values into this function, the x and the y's, and that would pop out the slope of this function at that particular point. But again, I could have the same solution, perhaps by plugging in this point up here, which would be at 2 and what appears to be 2 2/3, or up here closer to 2 6. So again, it was designed to get you the slope using both x and y as opposed to just the x values. Question to number 13. If we do this without doing the distributive property first, it'll eventually simplify this. It just looks a little different along the way. But it's about the same. Cool. 31. This one is our first one, I believe, that involves using a tangent line. I believe. So let's take a look at it. 13. Let's go to 31. We got it's the first one involving, yes. All right, we are supposed to find the slope of the tangent line to the graph at the given point. In this case, we're using a bifolium represented by x squared plus y squared squared equals 4x squared y. If you're truly bored one day, adjust some of these things and see what happens. Change it from a 4 to a 3, see what happens. Instead of a plus, change it to a minus, see what happens. There's some pretty cool little functions that appear. These are all different foliums. And you'll notice this version over here doesn't look exactly the same. There is a way to make these look very similar using fancy factoring. So, all right, let's do this. We're asked to find the slopes. Remember, my long-term goal is I actually want the slope itself at the point 1, 1. Now, before I begin, looking at our picture, let's form a hypothesis. What do we think our solution is going to be? Is it going to be positive, meaning it is increasing at 1, negative, meaning it's decreasing at 1, 0, meaning it looks flat at 1, undefined, meaning it looks going straight and down at 1. Because all these are possible in this picture, depending on where 1 is. Ricky thinks maybe 0. What do you guys think? Pretty good? I think that's a pretty good suggestion. Let's see if you're right. So Ricky says, I'm going to call you Ricky from now on. Spelled wrong. Ricky, say 0. Okay. So I feel like I spell it. You've never told me how you spell it, so it's the best you're going to get. All right. Derivative. If the problem says find slope, slope means derivative. So, left-hand side involves a chain. Right-hand side, a product. Let's do it. Left-hand side. The outer function is a square function. How do we take the derivative of something being squared?
2 inside stays the same.
What happens at the outside? -1. So 2 minus 1 would be a 1 up here. So right now that is a 1 power, but 1 powers don't do anything. Times. And I'm going to put that in parentheses. The derivative of x squared. Derivative of y squared. Very nice. Well done. Now already I'm looking at that and I'm sensing something nasty coming. Because y prime, the thing I'm going to want is right there. Something being multiplied to it, being added to it, and being multiplied to the outside of it. I sense a disturbance in this force.
I was going to ask if we can do the triangle rule in that.
The triangle rule?
Yeah.
Yeah. We totally could simplify this in the beginning.
Yeah.
Yeah. You could have applied this square at the very beginning. Would you like to make an amendment to this problem? Perhaps do that first. Let's assume your answer is no. All right, on the left-hand side, we have the left-hand piece is 4x squared. The right-hand piece is y. So left prime would be 8x. Right prime would be y prime. So what's happening on the right-hand side? Left d right plus right d left. So 4x squared y prime plus right d left. So 8x times y. Okay. Now, the creative ones can see some ways to make this problem a little bit easier, but there aren't much here. My goal, remember, long term, I want to get y prime by itself. I currently have a y prime on the left and a y prime on the right. Standard algebraic procedures. If I have a variable I want to isolate, it helps to get that variable onto one side and everything else on the other. First, I can then factor, distribute. Any of the algebra rules that exist, I can apply. But my goal should be I want to get both these y primes on the same side of this equation. Either they're both on the left or both on the right. And everything else on the other side. Suggestions?
So do we want to hold the right piece on the left side?
Okay, Ricky. A common suggestion. But I want you to understand what's going to happen if I do that.
It's going to be one on the top and one on the bottom.
I'm now going to have a y prime on top and a y prime on bottom, which would be the worst. Okay, the worst. Not worst or bad, the worst. I could divide this piece over, but it has the same basic problem. I don't get any closer to getting these two y primes on the same side. Other suggestions? We could. If we get to this point, we're like, oh my god, this is getting nasty. Oh, I'm not sure what to say, but we can always go back. Is that a suggestion you guys want to do?
Just subtract that piece over.
We could. Wouldn't get much better though. If we subtract this piece over, we end up with everything on this left-hand side. But again, my goal is long-term. Y prime be the only two things over here. I'd still have something being multiplied to this. Something being multiplied to the y prime. Something being multiplied to the y prime. Like I'm not getting any closer.
What do you see, Mr. Douglas?
What do I see? Two paths. I could go back to the beginning. It's not a bad suggestion. It just kind of hurts because you're like, I've already put work in. Please don't make me do that. Alternatively, the suggestion you don't want to hear. Boil.
Alright, back to the beginning.
It's too late now. You're asking my opinion. We're going for it. But my honest opinion, voting, I'm a dictator. Now, my honest opinion, as weird as it sounds, would be to divide everything by 4. Why would I divide everything by 4? Well, 2 would go away here, leaving a single 2 left over here. But I could factor a 2 out of both of these, meaning I end up with x squared plus y squared times x plus y times y prime. And on the right-hand side, if I divide everything by 4, this 4 goes away, this 8 becomes a 2. It doesn't make it much better, but it's a little better. Again, like, you're not going to get much out of this one without putting in some serious algebra work. So, I'm going to put in the algebra work. Ready? X squared times, I'm going to pretend I didn't see that. Again, it doesn't make the work much better. Okay, so I'm going to distribute the 2. This becomes 2x squared, 2y squared. Now I fold it through. 2x squared times 2x would become 4x cubed. 2x squared times 2y, y prime would become 4x squared y, y prime. 2y squared times 2x would become 4xy squared. 2y squared times 2y, y prime would become 4y cubed y prime. Okay? And the right-hand side doesn't do anything. 4x squared y prime plus 8xy. That's it. Squared. Okay. My goal long term, get all the y primes on one side. I have a y prime here now. A y prime here. Y prime there. I either need to move all the y primes on the left or all the y primes on the right and everything else on the other side. I could divide by 4 at this point. That wouldn't be too bad. Gone, 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 gone. 2. Seems fair. Okay. What we're going to do, all the y primes on the left, all the y primes on the right. Take it back now, yo. One hop this time? No? Come on, cha-cha. Fine. You know what? I like you guys.
Subtract the x cubed on the right side.
So moving all the pieces over to the right-hand side that do not include a y prime.
And then x squared y prime to both sides.
So he's saying we're going to move this piece to the left. This is y prime. This does not have y prime, so we're going to move this piece over here.
That piece as well.
And that piece as well. All right, let's get nasty. Let's try it. We'd have x squared y prime plus y cubed y prime minus x squared y prime equals 2xy minus xy squared minus x cubed. It's beautiful, I know. All right. Factor out a y prime, and then?
Divide everything off.
That's right. Factor out a y prime. X squared y plus y cubed minus x squared. Right hand side stays the same. 2xy minus xy squared minus x cubed. Y does not equal that. Y prime equals that. Okay. 2xy minus xy squared minus x cubed all over. X squared y plus y cubed minus x squared. So this is y prime. Great. We want the slope. So we got to plug in. So I'll take this equation, bring it over here. I want to find out what y prime is, specifically at the point 1, 1. So I take my function. Everywhere there's an x, I'm going to plug in 1. Everywhere there's a y, I'm going to plug in 1. So 2 1, 1, minus 1.
0 over 1.
Yep. But I have to show my work, sir.
0 over 0.
Not 0 over 0.
0 over 1.
Okay. X is 1. So 1 squared times 1 plus 1 cubed minus 1 squared. 2 minus 1 would be 0. 1 plus 1 minus 1 would be 1. Hey, Ricky. Good job. Now the picture, you can hard press to guess the answer is 0. So again, we just take our function, once we find the slope, we just plug in the 0.11 into that slope, and we get the slope from that point. Ready for me as well? So, how would this have looked? Just very briefly, if we had taken your suggestion, which I pointedly refused at the beginning, to just go ahead and pour this out. Okay, so here's the original problem. The original problem was x squared plus y squared equals 4x squared y. We can use the perfect square formula. The perfect square formula says if we have a plus b squared, this is a squared plus 2ab plus b squared from algebra 2. I can now plug in x squared and y squared, which will become x squared squared, which would be x to the fourth, plus 2x squared y squared plus y to the fourth equals 4x squared y. I now have a product rule here. That's not so bad. A product rule there. That's not so bad either. Basically, what it would do is it would shortcut us all the way to here. If we actually do this part, it'll actually jump all the way to here. It'll skip this boundary, so we have to just make decisions on what we need to do, which I think is nice. Like, I like it. It's kind of up to you. And yes, they do get the same solutions. For these kinds of problems, this puts us to the question of just how much are you willing to do for a certain problem in terms of the algebra. Are you willing to simplify it, or are you willing to FOIL it later? You gotta do one. So pick your poison. 33? Alright. 33. Which one's 33? Yes. Equation of a tangent line. Woo! You'll notice that some of these are named equations. Like the bifolium's a named equation, the witches of Agneris is a named equation. Like, what did you just say?
Volume of this Descartes.
Oh.
You got hurt.
I don't need a heart attack this early in life. Flume Descartes. Descartes is also a weird pronunciation for most people. Modern French people would call him Descartes, which is correct. Fancy math people call him Descartes, because that's the old-fashioned French word for it. It's all the same. Just don't say Descartes. Let me guess, you're a big fan of Euler, too. No? Euler? Never heard of Euler? His name is German, it's Euler. He's famous for a lot of geometry proofs. Would you like to know who went to a math convention and called him Euler because he didn't know how to pronounce his name? This guy.
That's why he's big on it.
Yep, you better believe it. All right, y minus 3 squared equals 4x minus 5. Okay, 33 is an example, so we're at the point, so we want the tangent line at 6, 1. 33 is an example of one where we could, in theory, solve for y. If we square rooted both sides, we'd have to do the plus or minus, so we'd have to do it twice. We'd have to add 3 to both sides, but we could do this. We have to do it twice, once for the top part of the function and once for the bottom part of the function, because we can't be certain without the picture of which one we need to plug this into. Okay? So this could be done without this rule, but we're going to do it with the rule. Now, just like on the previous one, we could simplify y minus 3 squared, or we could use the chain rule. I'm going to choose the chain rule for this one specifically, mainly because the chain rule isn't so bad. Now, on the right-hand side, I will simplify this. This would become 4x minus 20. Mainly because I don't want to do the chain rule on 4x minus 5. Ready? Left-hand side. Actually, that's a lie. Right-hand side is the easier one. I'm going to get that out of the way. The derivative of 4x would be 4. The derivative of 20 would be 0. Right-hand side is now done. Left-hand side. 2. Y minus 3 times y prime. That's a temptation, right? We've been distributing a lot.
It is temptation. Just divide it over.
Yeah, you better believe we're going to divide it over. Y prime is equal to 4 over 2 y minus 3. Also not typically the correct solution for this problem. Just because, well, if you can simplify it easily, you should. Yes. So what does this mean for this problem? The slope is entirely dependent on the y value. That's weird, right? But that's a natural consequence of this kind of function. If we had solved it the other way, we would have simply plugged in the x value and gotten a solution. It would just be a little different. Alright. We plug in 6. My goal is I want to plug in my point 6, 1. So everywhere there's an x, I'm going to replace with 6. Everywhere there's y, we replace with 1. We get a slope of negative 1. Again, everywhere there's this x, we replace with 6. Everywhere there's y, we replace with 1. There's no x's, so no 6's. Leave a single y, replace it with 1. Now, this will tell me my slope. I want the tangent line. My tangent line formula is on the board. Come out for 1. Y minus y1 equals m parentheses x minus x1. Standard formula for a line. Let's do it. Y minus y1. So 1 equals m. What is my slope for this function? Negative 1 times minus. All right, let's test this bad boy. So there's the picture. I'm going to put this picture into Desmos, and I'm going to put that particular function in Desmos. We're going to see if they're actually tangent. Let's do it. This is always a test you can do with tangent line problems. My original equation was parentheses y minus 3 squared equals 4x minus 5. Okay, looks pretty good. And now I type in my tangent line. Let's see if they actually are tangent. Y minus 1 equals negative 1 parentheses x minus 6. do you think? You must have done a good job. So I think that's the tangent line. What?
Just in case.
What?
Zoom in. Not gonna get it to me.
I had this fun buddy of mine who was one of those flat earther guys. Nice guy. Just he's one of those guys that happens to have a belief that contradicts my own. So I love showing him tangent line problems because I'm like, look, bro, the green line's clearly curved. The purple line's clearly straight, but if I zoom in far enough, they look the same. What's the deal? And he gets angry every time. Because math. Actually, he honestly doesn't care because that's the funny thing about beliefs. You can tend to ignore them if you just care hard enough. That green line is clearly straight. Flat parallel theory. Okay. Anything else from homework? We got about 8 minutes left. We did number 11, number 13, number 31, and number 33. Any other ones you guys want to see? Okay. This homework will be due tonight at midnight. Again, it's just the odd problems. And the solutions are posted at the very bottom. So if you get stuck, you can always make sure to check. So if I look at this one, number 33, I can clearly see that they wrote the other form of the equation. Y equals negative x plus 7, but it's fine. You were right. Answer 0. 31. Again, just the odds. Any questions? Or you guys want to see some of these even ones, maybe? Or I can just show in the corner. I love the asteroid. And again, I highly recommend if you get really, really bored, like take some of these really basic functions, like these famous functions, and just modify them some. You know, make this minus 8 instead of minus 6. See what happens. See if you can guess what's going to happen. Take these x cubes and make them x to the fourths or x to the fifths. See what happens. Because you might be surprised. But you gotta be pretty bored for that, so. Speaking of which, I'm pretty bored. X cubed plus y cubed minus 6xy. X cubed plus y cubed equals 6xy. It's so pretty. It's so pretty. I have, honestly, if you guys own one of the TI-84s like I own, I have never gotten one of these functions to graph properly. I'm sure there's a way, I just haven't found it. I probably could research it for a little while and find it without too much trouble, but I just never have.
What's happening at 0, 0?
At 0, 0? So the cool thing is, at 0, 0, this function is actually undefined. Because in one piece of the function, for example, this piece, so I have to split this up. At 0, the y value is 0. So the next question could be, what's the slope? Well, I propose you that the slope is undefined based on the basic definition of slope, which is that the left and right hand slopes have to agree. Now, from the left-hand side, there's two things that could happen. From this part, the slope is clearly 0, because it's leveling off. From this part, the slope is clearly 0, it's leveling off. but there's actually another place we can approach from, top and bottom. And the top is approaching undefined, and the bottom is approaching undefined, since they are approaching different values. One says approaching 0, one says approaching the undefined value. This defaults to undefined. This will also be the case if this approached any other set of values. Like if it just crisscrossed like this, it'd be undefined there. Simply because there's two different things happening at the same point. We're approaching two different sets of values at the same point, so the slope would be undefined by definition. Oftentimes, graphs like these are drawn in 3 dimensions, and so what happens is, at time 0, the slope would be 0. At time, I think it's like pi over 6, at time pi over 6, the slope would be undefined. Because what you do is, as you're drawing it, there's 2 different slopes, and so you can reference them by a third variable, z or time. And so at time 0, you have one thing happening at time 17 over 6. Pi over 7, something, something, blah, blah, blah. Over time it happens to be. They got a different slope. I just like, because cool things can happen if I just do this, change this 6 to a, 8. Oh, the loop got a little bigger. Ooh. Change this cube to a 5th power. Ooh. Change this cube to a 5th power. Ooh. Like, it's got some coolness to it. Like, come on. Okay. I guess I'll stop the recording. Reminder, it is due tonight.